Okay, so without further ado, now next speaker is an unconventional physicist, specialized in statistical mechanics, but has done a lot of works in several fields. Uh, Always very erratic, always very interesting, whatever he does. And now he's presenting a talk that I'm very curious about. That is about stylized models of sustainable human ecologies. Sustainability is something that is very important nowadays, and it would be very nice if our community of statistical physics could make a contribution. So please, Matteo, start.
Okay, thank you very much. Thank you very much for this kind invitation. Yes, so I understand this talk will be a little bit off the main topics of physics, but however, I believe it is anyhow connected to the spirit of Ising in the sense of trying to understand collective phenomena, and in particular collective phenomena which are say great interest. And I think the expertise of statistical physics is very much needed, and I hope to make this point. Okay, so this is joint work with Deborah Principe and Onofrio Mazzarisi, Simon Levin, Pablo Market, and others. And it all started with an initiative that we had a couple of years ago. We did some workshop on quantitative sustainability, in particular focusing on the human dimension of sustainability, because in the end there is a lot of work dealing with the technological aspects of sustainability, energy, climate, etc., which are closer to physics. But in the end, the real issue is, lies in many cases in the human dimensions, because even if solutions are there, then the issue is implementing these solutions. Okay. So, this is my motivation. So, essentially, that sustainability is a collective phenomenon, and humans are key players, and that there is something wrong in the way we think about this problem, because it's clearly looks like our planet is not going to go towards a sustainable future. And there are many crises, from the climate crisis, etc., that we are not really taking care of. And so what we plan to do is to step back and try to start thinking about these problems. And in particular, I will give you just two attempts to address these issues, or what is at the core of these issues. One has to do with trying to ask the question whether sustainability is in principle compatible with an open-ended innovation process. Okay, so the human species is a creative species. It invents new technologies, new ways of promoting its own growth by using natural resources. And so we want to understand whether this process can be at all sustainable. And the second question is essentially related to the fact that, most of our thinking in sustainability, but also otherwise, has to do with the utilitarianism, essentially the way we think in the Western world, essentially, where essentially profit more or less is always at the center. And we have more or less designed our world around this model of Homo sapiens, which is essentially Homo economicus. And there is plenty of evidence that this is not the right model. So I will try to introduce a different model, which I call Homo Felix, and to show you that you get quite different quite different behavior if you take this into account. Okay, so let me start. And okay, so the issue of sustainability it's a very long tradition, at least quantitative approaches to this. One place to start is probably Malthus, say 1798, and in his paper, well, what he observed is that the population is growing exponentially, and the food supply is only growing linearly. So essentially, at the end, we are going to have a problem because there's not going to be food for everyone. And so he was. This is what he was raising. Much later, there was this interesting paper. There were many papers, but one of these was a paper by von Forster et al. In Nature in 1960. And essentially what they did is to take the time series of human population over, say, more than 1 millennium, and they were fitting, they fitted this time series, and they found that the best model was this one. And this model essentially predicts that there is a finite time singularity on Friday, November 13, 2026. So, which is in 6 months' time. So we hope this paper is wrong, of course. But of course, I mean, this was also a catastrophic type of perspective. Then there were very influential works by different people stressing the fact that the planet is finite and that this imposes limits to the growth of population and of the economies. In particular, there was this very influential report of the Club of Rome, Limits to Growth. And this was followed up by several works, and in particular, one work has been taking a closer quantitative look to this, and they identified 11 different boundaries, or say red lines, and that we should not cross. And essentially, I mean, the quantitative analysis, they were showing that we are very close to cross many of these, and some of them might already have been crossed. So, okay, so now this raised a lot of discussion, especially in the community of economists, and essential, say, reply of economists is that this analysis was essentially neglecting the adaptation which can be achieved by market forces. So, in the sense that when some resource becomes scarce, the price goes up, so people move to other resources. So there is this substitution of scarce resources by more abundant ones. And also there is the technological progress. So there are ways of inventing new technologies to cope with with these finite limits. Okay, so the argument was that essentially it is not evident that you cannot have infinite growth even on a finite planet. And the idea is that essentially there are things like ideas that do not have limits, or are not limited. Okay, so then these arguments went on, and so what people realized is that actually the human population is not really, in practice, it has not been limited by finite resources, but it has it has been limited more by technological progress. So what I mean by this is that, in a pre-industrial revolution, pre-industrial times, essentially there was high fertility because essentially because there was a need for a lot of manpower. But then with technological progress, new technologies have been developed, and these new technologies were requiring a higher skill, and so there was a there was a decline in fertility due to the fact that there was a flight from to quality and to invest more in education and training of children rather than having many children. And this essentially was what essentially caused this demographic transition that many countries in the Western, many developed countries have experienced. Okay, so for example, in Italy, we are with negative population growth, and this is the same for many European countries. Okay, so then just to complete this picture on sustainability, I mean, this is a very maybe biased picture, but so talking about sustainability, there are different notions of sustainability. So there is a weak notion of sustainability, which is just related to human needs, and this idea of sustainability say depleted natural resources can be replaced by say manufactured resources, or say by engineered resources. And so essentially there is a way in which sustainability, there is a weak sense of sustainability where essentially the environment is not really needed. And it is a strong sense, notion of sustainability where essentially instead the ecosystem is essentially preserved. Okay, and actually the same is true for policy. So this statement, this Brundtland Commission was probably one of the first official approaches to sustainability, and their sustainability was defined as meeting the needs of the present generation without compromising the ability of future generations to meet their own needs. As you see in this statement, environment does not appear, essentially. So all this statement talks about are the needs of the human species. And when you talk about the needs of the future generations, this becomes a very, say, ill-defined concept, in the sense that if we think about our own needs seen from, few generations ago, our grandfathers could not even imagine what kind of needs we are having now. And so now, as you know well, sustainability now is defined in terms of these sustainable development goals. These sustainable development goals are essentially, as you see, they combine some. Most of the goals have to do with humans. Okay, no poverty, zero hunger, etc. Reduced inequalities, etc., etc. They don't have anything to do with the environment, but some of them have to do with the environment, like life below water, life on land, etc. So it is true that also there is a lot of quantitative approaches which have been targeted towards trying to include, say, these environmental resources, to give a value to these environmental resources. And this is particularly true for the field of ecological economics. But again, what is again in the at the core of this notion is always that natural resources should be valued according to human, say, utility, essentially. Okay, so this was more or less the background, and so what we decided to do is to look at a very simplified model, very basic model, where essentially we have these three components: the human population, natural environment, and a set of technologies. And essentially, the interaction between these three components is that essentially technologies require resources both from the population in terms of labor and from natural resources, but they also contribute to population growth, and they also deplete resources. Okay, so one way of putting these into quantitative terms is by this three set of equations. Okay, so Li is if you want, the amount of workers or biomass used by technology I, and essentially the growth of this technology is related to the availability of labor, which is by this term, which is N minus L, and the availability of natural resources, which is this other term, E minus E0. Okay, and then there is a decline term. So if this term is negative, then the growth is zero. Okay, and this L is the total, say, amount of people that are engaged in technologies. Okay, so this is the equation for the growth of technologies. Then there is the environment. The environment is a very classical dynamical behavior. So this is just the usual Lotka-Volterra, say, logistic growth with a certain carrying capacity, E0. And then there is a term which has to do with the harvest. The harvest, so the fact that these technologies, Li, they will use up the natural resources. Okay, And here we take this harvest function as being proportional to the environment, in the sense that the more the environment is depleted, the harder it is to extract resources from it. But similar results are also possible if you take other functions here. And finally, there is the population. The population has also a logistic growth, but in the logistic growth, the fitness receives a contribution from the technologies. Okay, so each technology promotes a little bit the growth of the population. Okay, so what we do is essentially we look at this model where these coefficients AI, BI, DI, and FI are essentially related by these ratios. Okay, and the idea is the following. So that so the idea is the following: that this leaves us three main parameters. One is the number of technologies that we have, which is essentially our measure of time. Another one is the ratio of how much technologies need population with respect to how much technologies contribute to population growth. And this is something which has to do with, which we can, is essentially a proxy for labor productivity. And then there is environmental impact, how much a technology impacts on the environment. Okay, and so we consider a situation where we introduce new technologies. There is a technological progress. I mean, there is a technological technology are discovered, and essentially for us, discovering a new technology just drawing at random these coefficients, say in particular AI and BI, because then the other two coefficients are given by these relations. And so we look at how the system behaves, how the equilibrium of the system changes as we introduce more and more technology, drawing them at random, okay, from a distribution. And of course, I mean, new technologies are random, but the existing technologies are not random, because essentially they invade the system only if if they satisfy this condition, because this is a condition under which this growth term will be positive. Okay, so essentially this is a interacting system where essentially the existing technology provides the constraint that determines whether new technologies will be viable or not. Okay, and so then what we do, we study this system, and we do numerical simulations, and also we solve exactly these equations in the limit when the number of technologies goes to infinity. And as you can see, so the self-consistent solution for these equations actually match very, very well the numerical results. So the analytic solution here is the yellow lines, and each point of different colors is a numerical simulation of the system, of this ecosystem, for a different number of technologies. You see let's say the violet is 10 to the 4, the light blue is 10 to the 5, and the dark blue is 10 to the 6. Okay, So let's see what is the behavior that we get from here. So first of all, what we see is that there is a phase transition. So when labor productivity is very low, below 10, there is a critical point at 10 here, we have a finite time singularity. So this is similar to this doomsday type of scenario. And this occurs because the feedback of technologies on population growth is larger than the decay term, and this causes essentially a finite time singularity. When we look at, when instead this labor productivity, this coefficient alpha, which measures this labor productivity, increases, and you are between 10 and 15, I mean, between these two critical points, we see that essentially the environment gets completely depleted, and when alpha labor productivity is higher than this, instead the environment recovers to the original value. The more technologies are included. Okay, so we have these 3 phases and these 2 phase transitions that we characterize analytically in detail. In particular, we characterize the scaling. So what we observe is that so in this scaling, in this intermediate region, the environment gets depleted as 1 over the number of technologies, whereas in these other in this second regime, what we call the strong sustainability regime, the environment converges to the pristine value E0 with a non-trivial exponent, which is minus 1/3. And what is really remarkable is that the phase transition is not related to environmental impact, but it is related to labor productivity. It's not related to how technologies impact the environment, but it is related to how technologies impact the population. And because if we look at how the environment changes as a function of environmental impact, we see that there is a smooth change. There is no phase transition here. And also we see that no matter what is the environmental impact, the more, this is a point taken alpha equal to 10, 20, so in this region here. Can you see my mouse, by the way?
Yes,
Antonio?
Yes, we do see it.
Okay,
Yeah.
very good. So you see that in this region, in this strong sustainability region, essentially the behavior is smooth, and the more technologies one introduces, the more the environment recovers. As far as the population is concerned, what we see is that this model features a demographic transition, and this demographic transition is induced just by labor productivity. I mean, there is no. We see a demographic transition without having to introduce to discuss about, say, the need for, say, higher skilled, etc. It's just that having a higher labor productivity leads to a situation where the population saturates. Okay, so here you see the population. So you see that in this weak sustainability region, well, in the doomsday scenario, population is infinite. There is no stationary state. In this intermediate region, the population is proportional to the number of technologies, grows with the number of technologies, whereas in the strong sustainability region, the population is essentially constant. And now, if you think of say doing an experiment where essentially the alpha, I mean this labor productivity increases is a function of the number of technology, as it has been, in the sense that what we have seen in the last centuries, that labor productivity has increased more than tenfold. Then the typical plot that you see is essentially a population that initially is increasing and then reaches a maximum and then saturates to a certain value. What we also see is what is essentially called the environmental closeness curve, which is also an empirically observed result, which is a little bit more debated, where essentially the say technological progress first degrades the environment, but then later on it improves it. Okay, and these all come from the solution to this rather simple model. Okay. Finally, what we see is again we see that this non-trivial strong sustainability phase is characterized by non-trivial scaling properties, and so in the weak sustainability phase, so the number of active technologies, the number of technologies which are really used, grows linearly with the number of technologies introduced. Whereas in this strong sustainability phase, it grows sublinearly. So this means that when one technology is introduced, this technology will displace other technologies which are less green in some sense, which has a higher impact on the environment. And this is seen by the fact that this threshold that determines whether a technology, I remind you about this threshold here, is the threshold for the parameter that tells how much of a technology is used with respect to how much the population is used. So higher threshold K, lower threshold K means greener technologies, so technology that use less of the environment. And so this parameter here decreases as you introduce more and more technologies. Okay, in this strong sustainable phase. Okay, so these are essentially the results. So I could spend a little bit more time on the numerical solution or the solution of these equations, if you want. But essentially, this was what I wanted to present in the first part. Okay, so the summary is essentially that open-ended technological process is compatible with strong sustainability, at least within this model, within this very simple model. And this simple model features phase transition between these three regimes, like a doomsday phase, a weak sustainable phase, like say living on Mars, and where essentially living on just engineered and manufactured resources. And then a strongly sustainable phase, which is characterized by this Schumpeterian dynamics of creative destruction, where the introduction of new technology displaces old technologies. So the quite interesting thing is that the key parameter is not the environmental impact, and the sustainability depends only on how technologies interact with the population. And the quite interesting thing is that this model features these demographic transitions and this environmental consciousness curve, and that essentially, so these conditions here are the conditions that already exist in many of our countries, in large part of the world, and so this means that sustainability is in principle, strong sustainability is in principle possible. I mean, this is what this model suggests. And this points to the fact that, well, in this model, what we assume is just like a mechanical interaction between the three components, these three components. So what happens in the real world is that the interaction between these three components is mediated by the economy. And so the real question is, what type of economy could achieve sustainability? Okay, so the final insight from this model is that essentially what this model suggests is that ensuring economic security, so making sure that people do not have to engage in labor-intensive activities in order to make a living, could indirectly foster sustainability by essentially increasing this alpha. So I would stop here and ask for questions, if there are, on the first part.
Okay, anybody raising hands? So while you decide if you do some question, Matteo, I have a question for you first, because I mean, it's a very optimistic model. Once you get something that is no dark, because nowadays everybody goes for Armageddon. But then to get to some kind of impact, I mean, for your model to be discussed, are there ways to make the parameters of your model more empirically founded? Even some metrics, like it seems that your sustainable regime, truly sustainable regime, has technologies that are introduced more like extreme events, right? But you have a good rate of extreme events, that you go beyond the tails, you get something better and better. So is there a way to make this more robust? Because, for example, one thing I think your talk shows that the model is very robust, is kind of structurally robust. So it should not matter so much what are the real parameters, but having an idea of the order of magnitude and something more convincing would be really great. Are you working in the direction? Do you have any ideas?
Yeah, no, thank you very much. So indeed, say connection to empirical data can only be at the level of collective variables, observables, like essentially, and it can only be at the level, at the qualitative level. It cannot be at the quantitative level, clearly. And so the idea of this thing, which is more or less in line with the work of Ising. I mean, in the sense that if you study the Ising model, you don't really predict the critical temperature. You don't really, but essentially there are say more specific problems, specific issues that, for example, critical exponents that you can predict. Okay, so probably one thing that one could try to predict or try to test with empirical data are the scaling behaviors. So, for example, by looking at patents, one could see what is the fraction, how the fraction of really used patents behave as a function of the total number of patents. Okay, so this could be one way to see whether there is some agreement at the qualitative level, in the sense that one would expect a sublinear behavior, in the sense that one would expect that the number of actively used technologies scales sublinearly with the number of technologies introduced. And there is some evidence of this. So, for example, if you look at the pharmaceutical industry, I mean, the rate of discovery of new drugs is extremely low, and the amount of and it has been slowing down quite dramatically. Okay, so I mean, with respect to how many, say, drugs are, say, produced or generated, to how many drugs are actually used in medicine. I mean, there is clearly a sublinear behavior, Okay. But yes, one could do. One could also look at this in more details. I think the more substantial contribution of this work is to point to the fact that maybe the emphasis on environmental impacts is not the right one, in the sense that one should really focus on improving the say labor productivity. Okay, so the fact that maybe, and this is probably something that is going to happen with artificial intelligence. So now we are all worried about the fact that artificial intelligence will displace a lot of works, but essentially this might not be a negative thing, okay, because it might mean that people will not have to do very labor-intensive works. I don't know if I addressed some of your questions.
Yes. I don't see any other hands raised. Just a comment, a general comment, because I think this is more an Italian initiative. In Italy, there is a tradition of what is called the civil economy.
I'm going to talk about that.
Oh, perfect. So I hope I'll see you at the conference next week. We will talk after. So go proceed with the rest of your talk. Thank you so much. Thanks.
Okay, very good. Very good. Thank you.